Hello everyone. Now we will continue our learning on simulation. Previously in the first section, we have created a reservoir model using MBAL software. We created a gas reservoir model. And then in the second video, we have learned about the creation. We constructed four typical gas wells that will produce the gas from the reservoir. Okay. And now we will construct production facility, production network, and we will model it using GAP software. Okay. And we are now inside the GAP. The software is really an interesting software. It's a production network modeling software. And with this software, with this modeling, we can integrate the reservoir model from Embal, well model from Prosper, and the network itself using this software. Okay, so first I will introduce you this software. As you can see, we have several tabs: file, options, view. Okay, here we can draw solid line connections and others, edit, flow assurance. If we want to put some constraints in our system, we can do that here. System constraints, generate. We can generate well IPRs, well VLPs, and so on and so forth. Later on, we will learn some of the features here: model validation, solve network, transient, prediction, results, reports, window, units. Let's check the unit. You can see we select oil field units. Okay. If you want to edit the units, select this one. Okay. The look is actually like what we have in MBAL, right? So for example, if you want to see diameter, so here the unit is in inches. Okay, we like that. Energy in MMBTU, million British thermal unit. Enthalpy BTU per pound, and so on and so forth. Gas rate in million standard cubic feet per day. Okay. Okay. Click OK. So for the units, we like this. Okay. Oil field unit. And to learn more about MBAL, you can open help, contents. Okay. You can open the index. All right. Search. Okay, I will close. New, to create new sheet. Okay. Open. Save the model. New window. Edit equipment controls. This is to run network solver. This is to edit the prediction script. This is to run the prediction. And this is the item that we have. First, we can install separator, join. Okay, we will use join a lot. This is to construct link, okay, or pipe, flow line, trunk line. We can use this icon. This is to model a well. All right. So the model we can put using this one and then connect it with Prosper. I will demonstrate that later. This is for tank or reservoir. This is the flare, pump, compressor, source or sink, inline element, inflow, Okay. Group, flow sheet, SJP. I don't know what it is. Oh, it's valve. Okay. Right click, delete. User defined inline element. Okay. Heat exchanger. Zoom in, zoom out, unzoom, mask, unmask, disable, enable, delete, move, select, unselect all items, find equipment on system window, all right? Production model, water injection model. Okay, we are now in production model, gas injection model, gas lift injection model, index, undo. Okay, so now first we will construct the big picture of our system. Okay, you can follow me. First, this one, add tank. Click tank. You can see add tank and put the model here. All right. So this is our tank. This is our reservoir. We can call it gas reservoir, for example. Click OK. All right. Gas reservoir. And click that again. Okay. So that we can have select in our cursor. Now I will put 4 wells here at well. 1, I call it well 1. And then 2, I call it well 2. And then 3, I call it well 3. And lastly, 4, I call it well 4. Don't forget to click this item again. Okay. And then I will connect my reservoir with these 4 wells, okay, to symbolize that these 4 wells are drilled into this reservoir, and these wells, okay, these 4 wells will produce gas from this tank, from this gas reservoir, okay. And to link that, I use this one, add link. Click, touch the gas reservoir, okay, hold on, left button, touch the well 1. Done. The connection already constructed. And then the second one, click, hold the left button, put the connection on well 2. Okay. And then for the well 3, all right. And lastly for well 4. Okay, so far so good. Click that again. Okay, I can move the pictures, the icons like this. Okay, and then I will connect the well, these wells, with the main flow line. Okay, or we can also call it header, for example, bigger flow line. Okay, and so that we, in order to be able to connect the well, we need join. Okay, join 1, and then join 2, join 3, join 4. Okay, first connect the well with these joins. Click, touch well 1, connect it with J1. Do that also for well 2, well 3, well 4. Okay, And then I will use, okay, I will move them a little bit. Okay, and then another join here. Okay, J5. And then I will connect J1 and J5 and also J2 with J5. And the connection between each join is actually represented by pipeline or flow line. Okay, so that in reality or in our imagination, we can imagine that the well, okay, will be connected to flow line, and then the flow line will be connected somewhere in the network. For example, they connect in manifold, and from the manifold to the station, they will flow inside bigger flow line or bigger pipeline. Okay, so let's construct the flow line from J1 to J5. Okay, so you can see the picture is quite different. Here we only have connection, okay, which is actually, it's not a pipe, it's just an imaginary connection between well and the joint. But here in J1 in J and J5, it's actually a flow line or a pipeline, okay? Flow line or pipeline. Okay, so it's not an imaginary connection, it's actual line, pipeline, or flow line. Okay, and also J2 and J5. Okay, so now I have one reservoir, 4 wells, and 2 flow line. Okay, connected in this joint. Okay, and then click that again. I want to put another join here, J6. And again, I will connect J3 and J6, J4 with J6. I will construct the flow line, the flow line. All right. And actually, we can change the name J5 and J6 with manifold. So I will select and then let me check. Can I double click the J5? Okay. Okay, so let's do that again. Close. Double click on J5. You see the label J5. I can change it to manifold underscore A. Okay, so I call it manifold A, and okay, I will drag them down and double click on J6. All right, I will call it manifold B underscore B. Okay, so far so good. Now I will connect manifold A with manifold B to represent another flow line. Okay. Usually this line will be bigger than the flow line from each well. Connect, touch manifold A. Okay. Hold the left button, connect it with manifold B. Okay. And also another join there. Okay. I call it separator joint. Okay, there. And I will connect the manifold B with separator join. I will rename it join. Okay. All right. Connected with flow line or pipeline. Okay. And lastly, from this join, I will connect it with the separator. and it is production separator. I will call it separator. Okay. Okay. Click that again. I will move the separator there. Okay. Click the move again. Now connect the separator join with separator. All right. Beautiful, right? So as you can see, we have constructed the big picture. So as I said before, I have one gas reservoir and I have 4 wells drilled into this well, into this reservoir. So I have 4 gas wells, and then I have flow lines connecting this flow line with the production network. Okay, so we can call it production network, production facility, production pipeline system. All right, I prefer network in this video. So the network, the center of the network will be the separator. Okay, so all the flows will be directed into the separator. The pressure of the system will be based on the separator pressure. Okay, so if you want to do production optimization, production debottlenecking, basically what you change or what you change is the separator pressure. Okay, of course, if the separator pressure is high, then the situation, we can call the situation back pressure, high back pressure. And we don't like actually the high back pressure because it makes the flow more difficult to flow. Okay, more difficult for the fluid to flow against the high back pressure. Okay, so usually we can do optimization by lowering the separator pressure. Okay, or lowering system pressure. If we lower down the separator pressure or the system pressure, at the end of the day, the wellhead pressure will be lowered also, will be reduced. And with lower wellhead pressure, usually we will have higher flow rate. Okay, so that's the concept. Okay, this is the first stage of our simulation. So far, so good. Now we need to connect this reservoir with the Eng-Man model that we have created. So double click. Okay, let's check it out. Label gas reservoir, name also gas reservoir if you want, model material balance. Okay, it's still inactive, but you can see the Eng-Man file is missing. So we need to fill this window, this model with Eng-Man model. So click browse. Okay, and then we will select the Eng-Man model that we have created. All right. Okay, this one, the file is gas reservoir Eng-Man. And as you can see, it is valid. This gap will read. And from the Eng-Man model, this software knows that the original gas in place is this number. Okay. And then the type is gas reservoir. Number of tanks 1. Tank ID is tank 01. Start of production in January 1st, 2008. Well connections okay. Constraints none. Injection fluid gas. Schedule none. Yeah, we can skip this injection gas. It doesn't mean anything. Okay, so from here, we can click input. We can leave them blank. Results. Later on, we will have results after we run the model. Input again. As you can see, we don't have production data. From the MBAL model also, we don't have production data. Compressibility, constraints, injection. Yeah, we can leave it as it is. Wells connected to well 1, well 2, well 3, and well 4. Okay. Schedule, we can leave it as it is. So we can click validate. Data is okay. Okay. Click check summary again. Okay, so far so good. Click OK. Okay, so you can see the gas reservoir is ready. All right, and also I will connect well 1 with the well model 1 created in Prosper, and also for well 2, well 3, and well 4. All right, open the well 1. You can see the label is well 1. Name mask is included in system. You can type in any comment here. I will comment well 1. Okay. Well type, I can change it to gas producer. Model VLP IPR intersection. Okay. Use volumes for red model. And again, I will browse and connect this well 1 with the actual Prosper model that I have created. All right. Okay, so this is the model. Tank connections okay. IPR and VLP still invalid. We will create or we will generate the IPR and VLP later in the gap software. No constraints, no controls, no downtime, no conning, no schedule. Check the input. Pressure drop control, none. In this control, IPR, yeah, we need to input some numbers in this IPR, but we can skip it for now. VLP, if you have a VLP file, you can connect it here. Conning, we can leave them blank. Constraints, downtime, tanks. Yeah, we connect the well with gas reservoir model. Schedule, we can leave it as it is. Results, later on, we will have the results written here after we run the model. Okay, so still we need to input the data here, especially in IVR and VLP. Okay, IPR and VLP, and in IPR we have IPR layer, more, and grid view. Okay, we can skip it for now. I will connect the rest of the 3 wells with the Prosper files first. Click OK. You can see well 1. And I will do that also for well 2, well 3, and well 4. Okay, well 2. Go to summary. Connect with my well 2 Eng-Man. Open. Okay, later on the IPR and VLP. Click OK. And also well 3. Go to summary. Browse. Okay. Find the well 3 Eng-Man. Open. Valid. Okay. Well 4. Browse. And then well 4 Eng-Man. Valid. Okay. So far, so good. I will check it first. It is actually gas producer. Okay. Double click. Gas producer. Okay. Gas producer number 4. Okay. All right. So almost ready for these 4 wells. Let's check if we open or double click this line. Okay, so basically, if we open this line, we will actually open the well. Double click. Okay. So as you can see, this is just an imaginary line, imaginary connection. So no real meaning here. And what if we open here? Yeah, nothing if we double click. It's just imaginary connection. But we can go inside this line because it's actually flow line. Okay, so double click. All right. Now let's check the summary. Okay, the summary, it's good. Okay, we can call it line 1, comments line 1. Okay, correlation, we can use petroleum exports 5, and others we can leave them as they are. Okay, environment okay, pipe data none, schedule none. Now we go to input. Okay, time since production started, assuming 100 days. And then for the overall heat transfer coefficient, 3. Oil heat capacity 0.53, gas heat capacity 0.51, water heat capacity 1. Okay. And then description. This is the main thing. Okay, this is the main thing. Open the drop-down menu. Line pipe with length. I will first change the length to kilometers. Okay, so I will close. All changes will be lost. No. Yeah, okay. Yes. Make sure you save, or later. We can do that later. Units, oil field. Okay. Edit units. For length, we go to length, L. Length, we change it, open the drop-down menu to kilometers, km. Okay, click OK. Go back to the pipeline 1. Segment type, it's line pipe. Oh, actually, we can change the unit here. Kilometer. 0.8048. TVD 0. Okay, so at 0 depth, inside diameter 4 inches with roughness 0.0006. Okay, so far so good. Enter elevation as, yeah, no TVD. And then rate multiplier 1, maximum length step 10,000 feet. Flow type tubing flow. Correlation, this is also important. I select petroleum exports 5. Okay, gravity coefficient 1, friction coefficient 1. All right. Now we can check this one, TVD 0 here. And environment okay. Environment okay. And then for the description, already okay. Matching, we can leave it blank. Constraint also, schedule also. Results later on will be populated here after we run the model. Click OK. First line ready. Now to the second flow line. Summary, we can call it line 2. Okay, line 2, correlation petroleum experts 5. Go to input, go to environment or description, or environment first. Okay, surrounding temperature 32, overall heat transfer coefficient 3, 0.5351. Okay, water heat capacity 1. All right, go to description. Now the line pipe also with length of 1.1096. Okay, and then the depth, the elevation of our flow line still on the surface. Okay, at 0 depth, the same inside diameter 4 inches, roughness the same. Okay, everything the same. Tubing flow, gravity coefficient 1, friction coefficient 1 also. Petroleum expert 5. Lift the constraint, lift the schedule, validate, data is okay. Click OK, click OK. Line 2, done. And then at the same, we do the same thing. Line 3. Line 3. Petroleum expert 5. Input, environment, 32 degrees Fahrenheit, 3. Okay. And then the description, the main thing actually. Again, line pipe. By the way, we can have choke, coated, flexible, or fitting. In this case, we install line pipe with length of 0.5 kilometers, 0, 0, 4 inches. Okay. Use as usual, no constraint, no schedule. Okay. Let's make it quick. This should be line 4. Okay. Line 4. Petroleum expert 5. Input, environment, 32. It's 3. Description, line pipe, 0.5, 0, 0, 4 inches. Okay, click OK. Now this line, okay, we call it summary, pipe, pipe, petroleum expert 5. Okay, input, environment, 32. This one is 3, overall heat transfer coefficient. Description, it's a line pipe, 0.3 kilometers, 0, 0 inside diameter. This one is bigger inside diameter. Yeah, that's why, yeah, because we connect the flow lines from several wells. Okay, so this pipe, this flow line will contain gas with higher rate, bigger volume. So that's why usually we use bigger size of pipe. Okay, we keep the roughness, everything okay, no constraint, no schedule, click OK. Lastly, for the pipeline between manifold B and separator joint, okay, pipe 2, petroleum experts, input, environment, 32, 3, Okay, this one 0,4, not too long actually. 12 inches. Okay, click OK. All right, so far so good. So now we can also set the separator. Open the separator. You can see first we have separator parameters. We assume water separated to be 100%, gas separated to be 100%. Okay. Constraints, this is the main thing. Okay. Maximum gas rate 250. So we set our system in such a way that the maximum flow rate that we have, that we operate, is only 250 million standard cubic feet per day. Okay, so that's our target. Okay, we give this information to our model, and yeah, the model will calculate it for us how the system can achieve this number. The model will recommend the operation system, the operation mode to us. Okay, we just give them this target. Okay, all right, to make sure it is 250 million standard cubic feet per day. Okay, we click OK. All right, we are almost done, but don't forget, we still haven't completed the IPR in each well. Okay, so double click on well 1, go to the IPR. Okay, okay, so now we will input this model with numbers. Okay, you can follow me. Layer type gas, the IPR type CNN. Okay, so actually, although we created IPR model in Prosper, we can also do that in the gap. So it's okay if we do that here, and we must do that here actually. By the way, if you have created IPR file from Prosper, you can also connect or take the file here by browsing it. Okay, but now I will just input numbers in this model. So let's say the C parameter, make sure the unit. Okay, this is 0. Okay, 0.008772. Okay, just to make it quite detailed, in reality, we just use maybe 3 numbers after the comma. Okay, but I just want to make it very detailed for example sake. Okay, all right. Layer pressure, reservoir pressure 5,300 with layer temperature 166. We can leave it blank. And then the condensate gravity 67 with gas gravity 0.77. Condensate gas ratio 22.2. Water gas ratio 1. And check the grid view. You can see it's automatically populated. Mask included, layer type gas, CNN, layer pressure, use IPR pressure drop, no. Okay. And others like this one, WGR, water gas ratio, condensate gas ratio, oil gravity, gas gravity, okay. All right. And also for the grid view, okay, more prediction fractional flow model, click edit if you want to edit it here. But in our case, we open the drop-down menu and use from tank model. Okay. Grid view, okay. Now you can see the layer 1 is okay. This section is okay. We use this fractional model or relative permeability from the tank model, from the M-ball. And the grid view already also okay. Again, abandonment, leave it as it is. No constraint, no coning, downtime 0, tanks, schedule, now VLP. VLP, we can construct the VLP by using generate, or we can also import if we have created VLP files from Prosper. Okay, I have created 4 VLP files from the Prosper, but let's check if we generate the VLP instead. Okay, I use allow left-hand side intersection for optimizer. Okay, this is proper calculation. We allow left-hand side intersection. Let's do generate. Okay, generate for gap model. Okay, for gap model. All right, follow Prosper file, the PVT method, generate. Let's wait. VLP generate finished, but some errors encountered during generation. Why? We need to be careful. Generate. Okay. That's why we need to prepare the second method, actually browsing the VLP files from the Prosper file. Okay. Browse this one. Okay. VLP1, well1 VLP. Okay. This VLP file is generated from the Prosper. Okay. Click open. Here. This one is better than generating it. By the way, let's generate if we can generate. Still error. So yeah, we will use this VLP. Okay, so far so good. Validate, data is okay. What is calculate? But we can skip it for now. This is actually if you have gas rate, WGR, condensate, gas ratio, and manifold pressure. What will you get for other parameters? Maybe we can do that later. Okay, so now we can click OK. Well 1 is ready. Go to well 2. Go to IPR. IPR layer. Still, layer 1 is invalid. Okay. IPR type CNN 0.00319334 with N 0.995. Okay. And then the layer pressure 5,300. Layer type 166. Condensate gravity 67. Gas gravity 0.77. Condensate gas ratio 22.2. Water gas ratio 1. Okay. Layer type. Yeah, gas. Okay. More relative permeability from tank model, from MBAL. Grid view automatically populate with data we have provided in IPR layer section. Okay, IPR is okay. Now VLP. Let's try generate again. Generate. Generate. Oh, still errors. That's okay. Click OK. Now we click browse. Tag well to VLP. Open. All right. Validate. OK. Click OK. Well 2 is ready. We do that also for well 3. Go to IPR layer. Okay, CNN, C is 0.00932. This is 0.957, 5,300, 166, 67, 0.77, condensate ratio 0.2, WGR1, okay. And then more, use tank model, grid view already populated, VLP, let's try again. Data, if you have, okay, if not, click OK, OK, or close. Generate, still errors. So again, we need to browse with and take the already prepared VLP file. Okay, click browse, take well3 VLP. Okay, validate. Okay, what if we check plot? Nothing here. Oh, wait a minute. Oh yeah, we can generate the VLP plot actually. Yeah, because we already have the VLP, right? TPD plot. So this is our VLP, pressure against the flow rate. Okay. The temperature. Okay. C factor, mixture velocity, erosional velocity, right? Maximum grain diameter. Interesting. Turner velocity. Okay. For liquid loading, right? Erosion flag, Turner flag, erosion rate, corrosion rate. Okay. Yeah. If you want to do calculation, yeah, you can calculate here. Let's say water gas ratio 10, just to check it. Water gas ratio 22.2, condensate gas ratio 0, manifold pressure 1000. What happened? Click calculate. Yeah, and the other will be calculated. So this is the flowing bottom hole pressure, will be calculated, flowing wellhead temperature, C factor, Turner velocity that is happening, Turner velocity. This is the critical velocity that is required in order to avoid liquid loading. That's the meaning of Turner velocity, this velocity. And others, Turner flag, erosion rate, corrosion rate, okay? So you can do the sensitivity, you can just try the flow rate, WGR, condensate gas ratio, or I think this should be 1, and condensate gas ratio is 22.2. Calculate, okay? All right, so far so good. And of course you can plot there, okay? And you can check the Turner flag, either you are safe or you are not, okay? Gas rate and Turner flag, or I mean Turner velocity, I should do instead. Turner velocity, this one. Yeah, okay. All right, so now you can close, click OK. Results, not yet. Click OK. And lastly, well for. Go to summary, input, IPR, IPR layer. Okay, don't forget well for. Okay, lastly, this is CNN 0.0562. This is 0.842, and then 67, 0.77, 22.2, water gas ratio of 1, more, the relative permeability from tank model, grid view, already populated. Oh, not yet, the layer pressure, 5,300 and 166. Everything changed to green colors. And again, lastly, the VLP, try generate, still not yet. Okay, still errors. Okay, so we will use the already prepared file. Click browse, choose well4, validate. Again, if you want to plot, all right. Okay, so we can close. Okay, so now we are actually ready to operate and to run the model. We can try once again, generate. Either we want to generate IPRs, but we already have that. Okay, let's check generate well VLPs. All, generate. Let's check it out. Yeah, still errors. So we will use the already prepared VLP files. Okay, so now check again the separator constraint. Okay, now we will run the prediction, or first let's check the solve network, not run prediction. Okay, what is if we do main? Okay, not yet. This is at source. What do we have here? Summary, input, separator, constraint. Okay, this is to run prediction. If we do next, here we will set the separator pressure. Okay, and we will set the separator pressure, the system pressure at 1000. But before doing that, let's check this. Back. Yeah, you can see if we highlight the line, flow rate of oil still 0, stock tank barrel per day, water still 0, liquid still 0, also still 0, 0, 0, right? Still 0, still no flow. Okay, so by running the model, we actually flow the system. Okay, we start the system until it reaches steady state operation. Okay, so here we will do steady state simulation. So after we run the prediction, we run the model, we will have the flow rate here in flow line 1, 2, in pipe 2, line 3, line 4. Okay, that's the meaning of this system to run. Okay, so yeah, we have the gas reservoir, we have 4 gas wells, we have the flow lines, we have the manifolds, we have the pipeline, we have the separator pressure, which will govern the separator system or system pressure. Okay, and let's check the result. All right. Okay, go to prediction, run prediction, start date. Yeah, we can start from January 1st, 2008. Step size 1 month. End date, let's say 10 years. So it will end at 2018. No DCQ prediction. Next, still 0. Next, separator pressure or the system pressure is 1000. Next, so the mode, no optimization, rule-based, optimize with all constraints, optimize with potential constraints only. For the basic case, for the easiest and the simplest operation, we start with no optimization. So the system, the gap will only give us the separator pressure of 1000 psig and the maximum flow rate of 250 million standard cubic feet per day of gas. Okay, so calculate. You can see the gap will run the EMBAL, the gap will run also the Prosper, and the calculation happens. You can see this is the error, numbers of iteration, the step. We are now in 2014, and the step maximum 122. Okay, so already done. It's quite fast. We can calculate, we can we can go to the main window, and we can also plot tanks or plot nodes. Let's plot tanks. What happened? Equipment type, tank, gas reservoir, plot, last prediction run, gas reservoir. Let's check the average gas production. Okay. So you can see this is what happened. Okay, you can also check the average oil production, the reservoir pressure. Okay, reduced from 5,300 down to 3,000 psig. Average gas production and others. Let's close it first. Main, still 0 stock tank barrel per day. Still not very good. I think it should change the results. Yeah, you can see we now have the results. Okay. And plot. So by operating the gap, we will have, yeah, flow rate or all conditions in each line, in each pipeline. So in gas rate, you can see pressure drop. You can know the pressure drop, right? It's very important. You can know the water rate. Interesting. Click OK. Yeah, usually we will have everything written here. So if we, yeah, touch this line, there should be flow rate of oil, something stock tank barrel per day, flow rate of gas also, and others. Or let's check the line first. This is for line 1. You can plot the gas rate. Okay, again, the pressure drop. You can plot many things. C factor, pressure drop due to friction, pressure drop due to gravity, pressure drop due to acceleration, right? It's important. But the most important thing is also of course the gas flow rate. Okay. Click OK. J3 also. Results. Plot. Liquid rate. Mass flow rate. Okay. Click OK. And line 4. Plot. Gross heating value. Okay. Pipe and pipe 2. Beautiful. Also the separator. This is the results for separator. Plot gas rate. Okay. Yeah, you can see we still cannot reach, or we cannot keep maximum flow rate of 250. Here we achieve 300. Although we said earlier that the maximum flow rate is only 250 that we will allow. So yeah, we can do the separator again, for example, change the input here, or we can do prediction, next, next, next. But now we will use either rule-based, we can try, or optimize with all constraints. Okay, calculate. So the gap will optimize the system with all the constraints that we give. Just want to check what will happen. Okay. So if you have many constraints, you can put all the constraint in the gap software and the gap will calculate it for us. So let's check the plot tanks, plot reservoir pressure, average gas rate, remove all. Yeah, still above 300. Still no difference. But regarding the results, I think we can, yeah, it's quite satisfactory. These results, the oil rate, the gas rate, water rate, and others, right? Yeah, so basically this is the network simulation. This is the integrated simulation covering the reservoir simulation using material balance with MBAL software and well modeling, well simulation using Prosper software, and the integration, the network simulation using GAP software. Okay, so it's quite easy, but of course you need to take some time to set everything up, the MBAL model, the Prosper model, also the GAP model. Okay, so I think we can call it a day. Maybe in the next section, we can discuss about other cases. Okay, but hopefully you already understand the sequence, the big picture of the integrated simulation. Okay, integrated petroleum simulation from reservoir simulation, well simulation, and network simulation, or production systems simulation, or surface facility simulation. Okay. Okay, but lastly, maybe, what if we solve network? Is there any difference? Yeah, we can have several pressure scenarios, but here we use only one. Next, no optimization, calculate, Okay, very fast. Now, yeah, actually, you have that now. So actually, you can do prediction and you can also do solve network. Okay, what I've just done is actually solve the network. Okay, and now after solving the network, you can see the results in each pipeline. All right, you have that. You know the flow rate across the flow line one. It is 100 or 1,823 stock tank barrel per day of oil. The water flow rate, the liquid flow rate, the gas flow rate, the pressure at this flow line, which is very important, and line 2, and line 3, line 4, and pipe 2, separator. Okay, so at this condition, you can get gas flow rate of 300 million standard cubic feet per day. Okay, and you can check the warning. Maximum gas rate separator constraint violated. 306 instead of 250 million standard cubic feet per day. Okay, so maybe you need to modify something so that you can reach the setting the maximum flow rate that you desire, which is 250 million standard cubic feet per day. Okay, so basically the current system, the current mode with separator pressure of 1000 cannot reach or cannot keep the flow rate at 250, but it can deliver more than that. It can deliver 306 million standard cubic feet per day. Okay, so I hope that's clear. So we can call it a day, or maybe lastly, if we plot gas rate, yeah, this is results plot for separator, or yeah, click OK. Results, detailed, all items. Okay, this is for separator pressure of 1000 actually. Okay, so basically with sulfur, you can do like this one. You can do 500, 800, 1000, 1200. And next, calculate. Main, okay. Bottleneck, yeah, you can see we have bottleneck in this flow line, maybe because it's too small, only 4 inches, but we can plot the results, detailed, all items. You can see like this one. So for example, for separator pressure of 500, we can get gas rate this much, 800 this much, 1000 this much, and 1200 this much. You can plot, you can see. So for gas flow rate and oil flow rate, if we increase the system pressure, of course, we will get lower flow rate, gas rate or oil rate. Okay. But as I said before, if you want to optimize the production, usually you can do that by lowering the separator pressure or lowering the system pressure. But of course, if you lower the separator pressure, later on maybe you will also have another problem, like the compressor power that is required to increase the pressure, okay, from the output of the separator to the sales system. Okay, but that's discussion for another day. But by doing the solve network, we actually do the sensitivity analysis. So solve network is actually sensitivity analysis, but the prediction is actually forecasting. Okay, so you can do either prediction or solve network or sensitivity analysis. Okay, so I hope that's clear. We already cover MBAL model, Prosper model, and gap model. All right, so that's all. See you again in the next lecture. All right.